Hello, hello everyone. Myself Krishna Kumar Karothiya, Assistant Professor in Department of Mechanical Engineering, IIMT College of Engineering, Greater Noida, UP. And today I would like to talk about the vapor compression refrigeration system. And the content of this lecture will be the vapor compression refrigeration system, vapor compression refrigeration system COP, volumetric efficiency, different type of vapor compression refrigeration system, subcooling in vapor compression refrigeration system, numerical on vapor compression refrigeration system. A few examples. The outcome of this lecture will be uh, the basic principle of vapor compression refrigeration system, and second is the different type of vapor compression refrigeration system and its COP. So if somebody is watching this video, he will learn these two things, and plus he can able to calculate the basics numerical on vapor compressor refrigeration system and COP of VCRS, power input in compressors, then heat rejection, refrigeration effect, mass flow rate of refrigeration. These terms the student can able to calculate. So if we talk about the vapor compressor refrigeration system, it have got the four component: evaporator, compressor, condenser, and expansion device. And you can see it have got two type of high temperature side and lower side. If you see the bottom one here, this from here to here, generally and the lower side it have got the low temperature, and here it has got the high temperature in refrigeration cycle. Okay, so evaporator generally at the low temperature side, and condenser generally at the high temperature side, or at the outlet of the compressor also is the higher temperature. So here you can have one, two, three, 4 point. Okay, so if we talk about the first component, which is fixed at the process 1 to 2, the compressor, here the temperature and pressure is increased as the isentropic compressor, and after that it reached at the point 2, and after that the vapor refrigerant need to be converted in the liquid state. So it passed through the condensation process, and latent heat of refrigerant being rejected to the atmosphere, and it converted to the liquid state, and after that it goes in the expansion valve or expansion device, where the temperature and pressure get decreased, and after decreasing the temperature and pressure, it goes in the evaporator, where it is used for the refrigeration purpose. Okay, here also, or you can say the evaporator coils. So this is the basic flow of refrigerant in the four component of vapor compressor refrigeration system, and generally 99 or 98% generally the refrigeration system we see today, or air conditioning system we see today, or used commercially, use the vapor compressor refrigeration system in refrigeration and air conditioning. And this is the schematic diagram of vapor compressor refrigeration system. Here you can also see the four component. In process 1 to 2 there is a compressor, 2 to 3 there is a condenser, 3 to 4 there is a expansion device, and 4 to 1 there is a evaporator, where cold refrigerated space or refrigerated effect is taking place with the help of the cold refrigerant. Okay, so in this piping system, the refrigerant being flow, and the whatever reaction or process I'm saying, it is happening to that refrigerant only. Okay, inside this piping system. Vapor compression refrigeration system can represent on TS and PS diagram to have the more knowledge about the temperature, entropy, pressure, enthalpy, and the designing of the refrigeration system. So here you can have the TS diagram, okay, where 1 to 2 is the isentropic process, 2 to 3 is the constant pressure heat rejection process, 3 to 4 is the throttling process, and 4 to 1 is the constant pressure heat rejection process. Okay, so here also the same process is being represented on the PS diagram. Okay, so basically vapor compression refrigeration system have four RTL process. First is the isentropic, second is the constant pressure heat rejection, and third is the throttling process, and fourth the constant pressure heat absorption. So how we can calculate the uh, COP of vapor compression? Okay, so we need to apply uh, the steady flow energy equations all these 4 points. Okay, 1 to 2 is it is the compressor, 2 to 3 is the condenser, 3 to 4 is the expansion or throttling process, 4 to 1 is the evaporator. So when we are finding out the COP, we apply the steady flow energy equation in these 4 points. Okay, so if we talk about this, what will be the enthalpy of this point? This will be H1. Okay, because okay, and this is will be H2. Okay, and this can be projected here on enthalpy scale. Okay, here, and here it will be H3 equal to H4 because it is the vertical straight line. So here it will be H3 equal to H4. Okay, and here the H1 is H1, H2, H3, H4. Okay, so this is the how we can represent the enthalpy over the pH diagram. Similarly, here you can also represent the entropy, like here the isentropic process means entropy remain constant. So S1 equal to S2. Okay, then here you have S3, S3 here you have, and here you have S4. It is the vertical line actually. So this is how you can represent the enthalpy and entropy over the entropy and enthalpy diagram. Now we need to calculate the COP of vapor compression refrigeration system. So how we can calculate the COP of vapor compression refrigeration? First, we need to apply the steady flow energy equation while neglecting the kinetic energy and potential energy. Okay, so as we know, the four components are there: compressor, condenser, throttling, and evaporator. So in that we can apply the compressor, we can apply the steady flow energy equation first for the compressor. So compressor is being fixed at the process 1 to 2, where H1 is the inlet enthalpy for the compressor, and WC is the work input in the compressor, equal to H2 is the outlet enthalpy of the compressor, plus Q is the heat being generated in the compressor. But we take the Q equal to 0 because isentropic compression. In isentropic compression, heat is generated as negligible, you can say. Okay. Then this WC become, here you can have WC become H2 minus H1. So this is how we can calculate the work input in the compressor. Second, condenser. So what is used for condenser? The heat rejection in the condenser basically taking place. So we need to find out here the heat rejection from the condenser. So we apply the steady energy flow equation. So at the inlet of the compressor is the point 2. So we write the enthalpy at the point 2 H2 plus what is the work of the condenser? The heat rejection. So the QR, the amount of heat rejected, equal to the outlet of the condenser, which is the point 3. So we write the H3 plus W, which is the work in the condenser. We assume that zero work or negligible work is being generated in the condensation process. So this equation become the QR equal to H3 minus H2 equal to uh, minus H2 minus H3. This is the sign representing the heat is being rejected from the system as the sign convention law from the thermodynamics. Okay, so this you can have the equation 1, and this equation 2 you can have. Okay, and this equation again, throttling process. So what is the throttling process? In throttling process, generally the enthalpy remain constant. Okay, so between 3 to 4 the enthalpy remain constant, and the enthalpy at the 3 point become equal to enthalpy at the point 4, so which is H3 equal to H4. Okay, so this you can have the equation 3. Okay, and the fourth component is the evaporator. So we apply here the energy flow equations. In that, the inlet of the evaporator is zero point 0.4, so we write the enthalpy at zero point 0.4 plus QA, heat absorption equal to outlet of the evaporator, which is the zero point 0.1, so enthalpy at the zero point 0.1 plus W, but the W is negligible for the process of evaporator generally. So we take W equal to 0, then this equation become QA equal to H1 minus H4, and this is also called the refrigeration effect. Or heat, what is the refrigeration effect? If we say the definition of refrigerant, the amount of heat absorbed in the evaporator basically. So what is the amount of heat is absorbed? H1 minus H4. So this equation become 4, and this is also called refrigeration effect. Okay, no, we know that COP equal to refrigeration effect divided by the work input. So we need to write refrigeration effect where it's taking place in evaporator, which is H1 minus H4. So we write COP equal to H1 minus H4 divided by the work input where it is happening in the compressor. So we write H2 minus H1. And this equation we can rewrite in term of H3, where you can replace H4 with the H3, because we know that H3 equal to H4 from equation 3. So we write this H1 minus H3 divided by the H2 minus H1. So this is the COP of vapor compression refrigeration system in term of enthalpy. Okay. Then you can have the power input to the compressor. So first we have already calculated the work input to the compressor, and if we want to find out the power input to the compressor, we need to have the mass flow rate. If we multiply the work input with the mass flow rate, then it becomes the power input. Okay, so here you can have the mass flow rate. If we solve with the help of the unit, mass flow rate, it is the kg per second, right? Unit second. Okay, multiply with kilojoule per kg. The enthalpy have the unit kilojoule per kg. Okay, so that this is the one method where you can find out the easily the equation for uh, power. So kg will cancel out. So this unit become kilojoule per second, and joule per second is watt basically. So this become kilowatt. So this is how you can find out the power input to the compressor. Okay. And similarly, you can find out the refrigeration capacity, which is also multiply with the refrigeration effect. Then it become the refrigeration capacity. So we take the M dash as the mass flow rate of refrigerant, multiply refrigeration effect, which is equal to m dot multiply H1 minus H4. This equation become kilojoule per second, and which is the kilowatt basically. Okay. So if we are writing the refrigeration effect in kilowatt, then we say this is the refrigeration capacity. Okay, and if we are writing in the kilojoule per in enthalpy form basically, so that called the refrigeration effect actually. Then we need to find out the volumetric efficiency of the reciprocating compressor. Okay, so how we can find out the volumetric efficiency of the compressor? First, we need to define the volumetric efficiency of the compressor. So it is the breathing capacity of compressor, and is defined as the actual volume of refrigerant entering to the compressor to the swept volume. Okay, so this is the definition, and how we can find out the equation for the this or volumetric efficiency. We need to take m dash as the actual mass flow rate of refrigerant, and small b is the specific volume of the refrigerant at inlet. Then actual volume flow rate will be mass flow rate of refrigerant multiply the specific volume. Okay, so this is the actual volume which is entering in the compressor, and now we need to find out the swept volume. Okay, so swept volume equal to the pi by 4 d square l. So this is the basic equation for the swept volume, where d is the bore diameter, l is the stroke length of the compressor. Where compressor you can make like this, or it is the reciprocating compressor. So this is the d is the diameter, and this is the l, which is the stroke length of the reciprocating compressor, or you can have the cylinder. Okay, so this l is the stroke length. If one cycle is completed and revolution per minute, then we can have the swept volume equal to pi by, here it should be like pi by 4 pi by 4 d square l n. Okay, so we need to multiply with the n, then hence the final volumetric efficiency will be eta equal to m dash is specific volume or small p divided by pi by 4 d square l and k, where the k is the number of cylinder, n is the revolution per minute, l is the stroke length, d is the bore diameter, m dash is the mass flow rate of refrigerant, and small v is the specific volume of refrigerant. So if we know these terms, you can find out the volumetric efficiency of the reciprocating compressor. Or if volumetric efficiency is given, then you can find out the size of the reciprocating compressor cylinder. Okay, so this can be calculated. Okay, now we need to uh, define the type of vapor compression refrigeration system. So there are three type of vapor compression refrigeration system. One is the simple vapor compression refrigeration system. Second is the wet vapor compression refrigeration system. Third is the superheated vapor compression refrigeration system. So first we need to understand how they are classified. So they are classified only on one point of location, which is the inlet of the compressor. And if the inlet of the compressor is the dry saturated point, like here on the saturation curve, okay, this point, then it is called the simple vapor compression refrigeration system. Then if the inlet of the compressor at the bed region, okay, then it is called the wet vapor compression refrigeration system. Okay, and if the inlet of the compressor at the superheated region, because here is the superheated, this is the wet, and this is saturated. So if this point is lie in the superheated region, it is called the superheated vapor compressor refrigeration system. Then there is the subcooling and vapor compression refrigeration system. So why the subcooling is come? So somebody find out the COP of vapor compression, then somebody say, oh, I can improve the COP of the vapor compression refrigeration system with the help of the subcooling. So okay, let's see how we can do the subcooling in the VCRS. So there are four components was there in basic vapor compression refrigeration system, and if we are doing the subcooling in VCRS, it will come, it will add the addition component which is called the heat exchanger basically. Okay, here you can see this. So in subcooling, the heat exchanger extra component will come in picture. So let's see how it is fixed. So what is the subcooling? Subcooling, from the name it is clear, to subcool the liquid refrigerant. Okay, from the condenser basically. Here you can see from 1 to 2, the compressor is compressing the refrigerant at the point 2, then it phase change taking place from 2 to 3. Okay, then 3 to 4 or 3 to 3 days, you can see the slightly temperature is decreasing of the refrigerant while passing through the heat exchanger basically. Okay, and while passing through this refrigerant in the heat exchanger, it come in the contact of this line. Okay, so the heat exchange take place in these two uh, temperature refrigerant. Here it is the being hot temperature, and this line is the low cold temperature, cold refrigerant, which is coming from the evaporator. So heat will transfer from the high temperature refrigerant to the low temperature refrigerant, and this temperature, here you can also see on the TS diagram, this and this. So 3 to 3 days the temperature is being decreased, and this decrease in temperature is called basically the subcooling in the vapor compression. So what, how the COP is increased with the help of the subcooling? You can see if this heat exchanger is not there, suppose. Okay, then what happen? The expansion will take place from this 3 to 4 point, and this will be lie somewhere here. Okay, it will not reach here. So the length of the evaporator, you can see, will reduce to here. Okay, 4 to 4 days you can have. Okay, this is suppose 4 days, so this being reduced to the 4 days, and this, if this length is reduced, then what will happen? The refrigeration effect is decreased. Okay, or refrigeration effect is small. Okay, so if we apply or use the subcooling or heat exchanger in the PCRS, then this 3 point being shifted to the 3 days, and this 4 days point will be shifted to the 4. So you can see the refrigeration effect will increase from 4 days to 4, and this will increase the COP of the uh, vapor compressor refrigeration system, and this is the advantage for the subcooling. And you can also see the refrigeration uh, superheat is also increased, or it is being supplied at the 1 dash point. Okay, so this is how the subcooling is work. So you can see here 3 to 3 days the heat is loose in the subcooling, and this heat where it's going from the 1 dash to, here you can see heat exchanger 1 dash to 1, 1 to 1 dash. So heat gain will be taking care here, 1 dash 1 to 1 dash, and heat is losing from 3 to 3 dash. So if we apply the energy conservation law, then heat loss equal to heat gain, which will be the enthalpy of subcooling will be equal to enthalpy of the uh, superheating. Okay, or heat loss will be equal to heat gain. So this we will see in the next slide. Here you can see subcooling in VCR. We know that heat lose equal to heat gain. So heat we are losing in the subcooling from 3 to 3 dash. So this become H3 minus H3 dash equal to H1 dash minus H1, which is the heat gain. Okay, so this become the enthalpy equation for the subcooling. In term of temperature, this can be right, the CPL is specific heat for liquid refrigerant in bracket T3 minus T3 dash in bracket close equal to CPV specific heat of vapor in bracket T1 dash minus T1. Okay, so this is the subcooling equation in terms of temperature, and here you can see that T3 minus T3 dash is called the subcooling degree of subcooling, and T1 dash minus T1, this is called the superheating or superheat. Okay, so this is how the subcooling is taking place in the VCRSs. Okay, so based on the COP of vapor compression, then subcooling, power input to the compressor, volumetric efficiency, you can have the few numerical, which is this is the exercise for the student. They can solve their own and these numerical to clear the basic concept of the vapor compressor refrigeration system while referencing this lecture or after watching this lecture. So here the few numerical for the uh, better understanding of the concept. The first, second, or third numerical, a student can solve these numerical to have the better understanding. Okay. Here I have also included the solution of these numerical. You can have the glance of the first question where I have asked the find the COP and power input in kilowatt. Okay, so they have given some enthalpy for the vapor compressor. Okay, and they ask to find out the COP and power input in the compressor or refrigeration system. So this will be, they have given the enthalpy at the point 3 and 4, which is 75. At the inlet of the compressor, they are given the enthalpy 183 kilojoule per kg in the question 1, and H2 equal to, or outlet of the compressor, they have given enthalpy of 210 kilojoule per kg. To find out the COP, we know the equation for COP equal to H1 minus H4 divided by H2 minus H1, which is equal to, we will put these value in this, and this becomes the 4, the COP of the this. And we know that COP equal to refrigeration capacity divided by the power input. And in this question, they have given the uh, refrigeration capacity, which is 5 kilowatt, and COP we already find out, so we can find out the power input in the refrigeration system, and which will come around 1.25 kilowatt. So this is how the simple calculation is being done on the vapor compression numerical. Okay, here again this is the second question solution, and here you have can have glance. Okay, and student can solve this their own by taking the reference from this slide. Again, there again the third numerical solution. uh, the student should solve their own numerical while taking the reference from this slide. Okay, so thank you very much for watching this video. I hope you liked it. Thank you all of you. Have a nice day.